Okay, so today is the 9th lecture in advanced course in classical logic. We continue the topic of the previous lecture. The previous lecture was technically more difficult than other lectures, but today we do not need almost all of the details, of the technical details. We only need the main fact that we proved on the previous lecture. So, on one of the previous lectures, we studied what is a filter and what is an ultrafilter. So today, filters and ultrafilters will be denoted by phi. And the last lecture was devoted to building ultraproducts. So if we have a family of models indexed by some index I, and we have phi, which is an ultrafilter over I, then we can build first a product and then an alter product of these models. Usually it is a much bigger model. And the main property of this new model, so here it is denoted by M, here by N. Well, it doesn't matter. By M. By N, it should be more convenient. So if we have an alter product of some models, but what are models? Models, each model is a set and an interpretation of some symbols, predicate symbols, constant symbols, and functional symbols from some signature. We will denote a signature by sigma. It will be a fixed signature, so a fixed some signature sigma. We have predicate symbols, functional symbols, constant symbols, and all models are over this signature sigma. All formulas are over this signature sigma. So I will not mention sigma later, so it is fixed for the whole lecture. Then for any closed formula, it is true in this big model if and only if the set of indices I, such that A holds in Mi, is an element of the filter, of the ultrafilter. It is important that phi is an ultrafilter. What is an ultrafilter? It's a collection of some subsets of I, such that the empty set is not its member, the whole set I is its member, phi is closed under taking supersets. If X is its member and Y contains X, then Y is its member. And the phi is closed under intersection. If two sets belong to phi, then intersection of them belongs to phi. And this is only the definition of filters. Ultrafilter is a filter such that for every set X, either X is in the filter or the complement is in the filter. Okay. So this is the main thing. So in words, we can say that A holds in the alter product if and only if A holds in almost all models Mi. If all models Mi are just the same model M, then this alter product will be denoted by this notation, M phi, and this will be called the ultra power. I did write the word here, the ultra power. And for ultra powers, the consequence of this theorem is if a formula is true in the ultra power, in the original model, if and only if it is true in the ultra power. Because if all models are the same, then this set of indices where A is true is either empty or the whole set I. So either A is true in M, then this is I, big I, or A doesn't hold an Mi, then it is empty. Okay, so this is the corollary. So in other words, we say that M, the model and its ultra power are elementarily equivalent. They satisfy the same sentences of this signature. Okay, this is the only thing that we need to know from the previous lecture. We will use this technique for obtaining important results. So these are the fundamental results. Today we will consider the fundamental results in mathematical logic. And firstly, we define the notion of a compact class of models. So mathematics studies different structures, groups, fields, topological spaces, linear spacers, and so on. And some classes of structures of this kind may be called compact. What is a compact class of models or of structures? So a class K is called compact if for any set of formulas, of closed formulas, I will always consider closed formulas, so I don't write this word closed. If every finite subset of gamma has a model in K, then the whole set has a model in K. So has a model in K means that there is a model M that belongs to K such that gamma is true in M. So this is a compactness theorem, but relative to the class K. So there is another term, G has a model in K. We also say that gamma is satisfiable. So we can say the class K is compact if and only if for any set of formulas gamma, if every finite subset is satisfiable in gamma in K, then the whole set gamma is satisfiable in K. So this is the basic definition. Some classes are compact, some are not. There is a more convenient definition, but equivalent definition of compact classes. So we consider here any sets of formulas, and here we will consider sets of formulas that are closed under conjunction. Closed under conjunction means that if we have two formulas in gamma, then their conjunction is in gamma. Therefore, if we have finitely many formulas, A1, AN in gamma, then their conjunction with any parentheses is in gamma. So then the definition says, for any set of formulas gamma that is closed under conjunction, if every formula is satisfiable in K, then the whole set gamma is satisfiable in K. So we don't need finite subsets. We only need one formula here, which is more convenient in the proofs. So these are two definitions, and just an easy argument shows that they are equivalent. From 1 to 2. So assume that we know that K satisfies 1, Y it satisfies 2. So we take any set of formulas gamma closed under conjunction and assume that the first line holds. So every formula has a model in K. Why the whole set has a model in K? So we need to use definition 1. In order to use definition 1, let us take any subset gamma, finite subset delta. It has formulas A1, AN, for example. And let us build their conjunction. Then this conjunction is in gamma because gamma is closed under conjunction. So by this definition 1, by our assumption, this formula has a model in K. It is satisfiable in K. But the formula A or the set delta is satisfiable. It's the same because A is just a conjunction of delta. So we apply our definition 1 and obtain that the whole set gamma has a model in K. Is satisfiable in K. So this is very easy. This is most probably an exercise. I should leave it as an exercise. From 2 to 1, how can we do? So here we talk about sets closed under conjunction, and here about arbitrary sets. So let us take an arbitrary set, any set gamma, take a finite subset delta that has a model. How can we use definition 2? We don't have a set of formulas closed under conjunction, but we can take a new set of formulas, the closure of gamma under conjunction. So all possible conjunctions of formulas from gamma. So this new set, gamma conjunction, will be bigger than gamma. It will contain all conjunctions. But semantically, it is the same. If we take conjunctions, we don't introduce any new conditions on the models. For any model M, it satisfies gamma if and only if it satisfies gamma conjunction. So for models, it doesn't matter. And therefore, we will use definition 2 as assumption. So each formula has a model in K. Because if we take any finite subset, so any formula in this new set is a conjunction of some formulas from the original set of finitely many formulas. And these finitely many formulas form some finite subset, which has a model by our assumption. So gamma has a model. Well, it's more easily to write the proof yourselves than to listen to the proof or to read the proof. So it is an easy exercise. Okay. So the main application of ultraproducts is the following. If we have a class of models that is closed under ultraproducts, then it is compact. And compactness for various classes is very important, very useful notion. It allows to obtain some new results. What does this first line mean? A class of models closed under ultraproduct. So if we have many models mi in K, then and any ultrafilter phi, then the ultraproduct of these models, modulo phi, is again in this class K. So like as in usually in mathematics, closed under something means that applying this operation doesn't take us outside K. So we remain in K. So let us see how we can obtain this. So we want to obtain that K is a compact class. So let us go by definition 2, where we have sets closed under conjunction. So we need to verify the definition 2. So take any set of formulas closed under conjunction. They are indexed by some set I. Well, in the definition of compactness, if gamma is finite, then in both cases it is trivial, because for every finite subset delta, we can take delta equals gamma, and so the only interesting case is when gamma is an infinite set. So in general, if we have a signature that is countable, we have countably many predicate symbols, countably many functional symbols and constants, then the set of formulas is again countable. And therefore, infinite gammas simply means countable gammas. So the only interesting case in these definitions, definition 1 or definition 2, is when gamma is a countable set of formulas. So in this line, we could write gamma is a set of formulas AI, where I ranges over natural numbers. But I will write simply I, it doesn't really matter. Moreover, this will, so our proof will also hold when we have more powerful signatures. We can have uncountable set of predicate symbols, uncountable set of constant symbols, and still our proof works. So I is any set of indices. Okay, so gamma is a set of formulas closed under conjunction. So let us work with this set of formulas. So assume that every formula has a model in K. Let us denote this model by Mi. So in the model Mi, the formula AI is true. How can we build a big model, some model M, in which the whole set gamma is true? Of course, by ultraproducts. But for ultraproducts, we need not only models, but also an ultrafilter. How can we build an ultrafilter? First, we consider these subsets of I. We denote Xi, the set of indices, L, such that in the model number L, the formula AI true. So we fix formula AI and consider all models where this formula is true. So this is a subset of I. And we want to build an ultrafilter that has these sets as elements. But what do we need to check for this? We need to check that this set of the family of these sets has the finite intersection property. The finite intersection, the intersection of finitely many sets of this kind is non-empty. So we take finitely many sets, xi1, xin. Why it is non-empty? We need to give an example of an element of this set. This will be the following element L. So each set corresponds to some formula AI. And then we can take these formulas AI, take their conjunction, denote this. So it is again an element of gamma, so it has some number, some index L. So this L will be the index that we need. So why this L belongs to the intersection? Because in the model ML, this long formula is true, this long conjunction. In particular, each formula AI1, AIN is true. So this L belongs to each of these n sets. Okay, we have verified that this family of sets has the finite intersection property. And then by the standard result, this family of sets is contained in some ultrafilter. And now we are ready to build our big model. We build the ultrafilter, the ultra product of our models, MI, over modular this ultrafilter phi. Let us prove that this is the model that we need. In this model, our gamma holds. Firstly, recall that this model belongs to K because K was closed under ultraproducts. So we need a model for gamma that belongs to K. And for these properties holds. This model belongs to K. So, okay, it remains to show that in this model, all formulas from gamma hold. So we need to show for every formula AI why this formula holds in this big model. And here we, for the first time, use the main result about ultraproducts. AI holds in this model if and only if the set of indices where this formula holds belongs to ultrafilter. Let us consider the set of indices L where this formula holds. Why is it an element of the ultrafilter? Because it is exactly Xi by our definition. And Xi is an element of filter. That's it. So this is perhaps the main tool. So the main technical trick was done here. And in the next theorem, we will simply use this principal result and obtain some consequences. What is the main question? So here it is a corollary, the Maltsev theorem. So for example, take the K to be the class of all models. Of course, it is closed under ultraproducts. If we have many models, then the ultraproduct is again a model, is again a structure. It's a trivial. So the premise is trivial, and we obtain so simply that the class of all models is compact. In other words, the compactness theorem holds for the class of all models. So this is the usual formulation of compactness theorem. If every finite subset of formulas is satisfiable anywhere in any model, then the whole set of models is satisfiable, again, in any model. But here we have even more, not only for all models, but for any other classes that are closed under ultraproducts. So here we have more. Okay, the main question in mathematical logic, in various branches of mathematical logic, is can we axiomatize some class of structures? We are interested in some class of structures. Can we write formulas that define exactly this class? If we can, this class of models will be called elementary or axiomatizable, or sometimes first order definable. So it is elementary if there is a set of formulas gamma such that K is exactly the class of models of these formulas gamma, So in other words, for every model M is in K if and only if M satisfies gamma. For example, the class of groups. We know that this class is defined by 3 first-order formulas, 3 axioms of groups. Similarly for fields, for linear orders, for Boolean algebras. Moreover, the same holds for infinite groups, because we need to take the axioms of groups and the following axioms. There is at least 2 elements, there is at least 3 elements, and so on. We will have infinitely many formulas. It doesn't matter. Here, gamma can be infinite. But these formulas, together with the axioms of groups, will define exactly the class of infinite groups. Well, and there are other examples. Algebraically closed means that every polynomial has a root. So we, to formulate this, we need to say that for every polynomial of degree 2, for every a, b, c, the polynomial a x squared plus bx plus c has a root. Every polynomial of degree 3 has a root, and so on and so on. So for every degree, we need an additional axiom, a separate axiom. Again, we will have infinitely many axioms, but this doesn't matter. This class will be axiomatizable. But we will see later at in the second part of our lecture that the class of finite groups cannot be axiomatized. It is not elementary. The class of finite groups, finite linear orders, finite fields, and so on. So we need a technique, a method of proving that some class is not elementary. So we need some necessary and sufficient conditions. When a class of structures, a class of mathematical structures is elementary, and when it is not an elementary class. We need necessary and sufficient conditions, but conditions of what kind? Usually in results of this kind, conditions are understood as conditions of closure under some operations. So if we say that a class K is elementary if and only if K is closed under this operation and this operation and this operation, and possibly relations closed under this relation and this relation between models. And this will be a theorem that we want. So conditions are in some sense structural conditions. So we need to say that this class or its complement, the class of models that are not in K, is closed under some operations or relations. So this is what we are looking for. But what we already know. First, we know that every elementary class of models is closed under ultraproducts. This is a direct consequence of the Wash theorem. Why? Assume that the class K is elementary. It is defined by some set gamma. Then assume that we have many models that are in K, so they satisfy gamma. Then we take the ultraproduct by Wash theorem. Its the ultraproduct again satisfies gamma, so it is in K. So this is an immediate consequence of the main theorem about ultraproducts, the Wash theorem. What else do we know about elementary classes? We also know, this is an easy exercise, that it is closed under elementary equivalence. Elementary equivalence, that means that two models are elementary equivalent if they satisfy the same formulas, the same closed formulas. So assume that M is a class, is a model from K. So this means that M satisfies some gamma. And assume that M and N are elementary equivalent. Why N is in our class K? Because it satisfies gamma. We transfer gamma from M to N. So we already know that elementary clusters are closed under ultraproducts and closed under elementary equivalence. So these are necessary conditions. It turns out that these two conditions are sufficient. Not only necessary, but also sufficient. So this is the fundamental result in model theory, Kessler's theorem, or axiomatizability criterion. So a class of structures of some signature sigma is elementary if and only if it is closed under ultraproducts and elementary equivalence. On this slide, we have all details of the proof. It is quite short proof, just on one slide, but I will only give some basic idea, and we will not go into details. So assume that the class is closed under ultraproducts and elementary equivalence. We want to show that we can define this class by some set of formulas gamma. What is a natural candidate? Which formulas can we take? Of course, these formulas must be true on the class K, on every model from K. So let us take all formulas that are true on K. Maybe they will be sufficient. So let us take all formulas A, closed formulas. Everywhere in the lecture, we have closed formulas, such that they are true in all models from K, denoted by gamma. And it is really so. So this this set of formulas will exactly define our class K. So we will prove that K is exactly the class of models of this gamma. One inclusion is trivial here, of course. Which one? So if we have any class of models, we take all formulas that are true, so all laws of this of these structures, and then consider all models where these laws hold.
Well, I guess that's that K subset of models of gamma is a trivial one.
Yes, this is trivial, and this even holds for any class K. We don't need these assumptions of our theorem. For any class K, if we take its theory, then its models, we of course obtain all models from K and possibly some other models. For example, if K is just one group, we take all laws that are true for this particular group. It's the theory of this group. And then consider all other groups that satisfy the same laws. Of course, we obtain this group, so we obtain K, and possibly others. Of course, we will obtain others groups, for example, all direct products of groups of this group, ultraproducts, and so on. So we only need to prove the converse application. What does it mean to prove the converse? Take any model from the right hand side. So take any model where gamma is true. Why it isn't K? In this model M, besides gamma, there are some other laws. So M satisfies these laws, but it may also satisfy some more laws. So let us take all laws of this particular model M. And then we prove that T has a model in K. So there is some structure in K that satisfies exactly these laws, the laws of the model M. We use compactness here. So there is some model that satisfies exactly these laws, the laws of the model M. But what does it mean? So we had a model M, T is its laws, and then we have a new structure that satisfies these laws. We claim that these two models are elementary equivalent. So by construction, we only have that if some formula A holds on M, then it holds on it holds on N. But in fact, it is if and only if. So one direction is by construction. If A holds on M, then A holds on N. The other direction is easy. If A doesn't hold on M, then its negation holds. And then we can proceed as before and obtain that it doesn't hold on N. So if and only if. So they are elementary equivalent. And therefore, since N is an element of K, M is again an element of K because K is closed under elementary equivalence. So in the proposition 1, we used that K is compact. That K is closed under products implies that K is compact. And in the proposition 2, we use that K is closed under elementary equivalence. So this is the, in fact, here we have the complete proof. So you can simply stop the video and later and read what is written here. Okay. Another question is, can we define our class of models by finitely many axioms? But since we have conjunction in our language, finitely many simply means we can define by one axiom. We can simply take the conjunction of axioms. So we write definition as follows. The class of models is finitely axiomatizable if K is exactly the class of models of this one formula. So for any model M, M is in K if and only if M satisfies A. Now, the natural question is, which clusters of models are finitely axiomatizable? We already know when it is axiomatizable by the previous theorem. What do we need to add to the previous theorem to obtain finitely axiomatizable classes? So this was our previous theorem, just to compare. The new theorem says the class K is finitely axiomatizable if both the class K and its complement satisfy the previous theorem. So we can write K and its complement are axiomatizable. Well, one direction, of course, is trivial. If K is finitely axiomatizable, then of course it is axiomatizable. So if K is axiomatizable by some formula A, then it is axiomatizable. And the complement is exactly axiomatizable by the formula not A. So A is a closed formula. We can take, so K consists of models where A is true, and its complement consists of models where not A is true. So this is easier. Both classes are even finitely axiomatizable. Okay. The converse. Assume that both classes satisfy these conditions of the previous theorem, so they are both axiomatizable by some possibly infinite sets of formulas. Here we have gamma, here we have delta. So we have two classes axiomatizable by some sets of formulas, but they are complement of each other. So if we take formulas from gamma and delta together, gamma union delta, they cannot have any model, because models that satisfy gamma are in K and models that satisfy delta are in the complement of K. They don't have common models. So the union of these two sets does not have a model. So by compactness, by Maltsev's compactness theorem, there are finite subsets that such that gamma prime and delta prime are not satisfiable. Let us denote gamma prime A1 AM and delta prime B1 BN. So they are finite subsets, and their union has no models. Then we claim then that the class K is defined exactly by gamma prime, and so by conjunction of these formulas. Well, simply because gamma prime is a subset of gamma, so the class of models of gamma prime is bigger than here, than K. And the class of models of delta prime is bigger than the complement of K. But we cannot go bigger because the models of gamma prime and the models of delta prime do not have common models. So we must remain inside K, and we must remain inside K, the complement of K. So this is how to prove this. So this is an exercise. We still obtain the same class K in the same class, the complement of K. Okay. Well, here are the technical details, of course, of these theorems, but the main thing is to know how to use these theorems. So now we will consider some examples. Which classes are compact, which are not, which are axiomatizable, which are not, which are finitely axiomatizable, and so on, which are not. And in these constructions, non-principal filters are very important. Let us recall what is non-principal filters, and we will only consider filters and ultrafilters over natural numbers. For our purposes, this is sufficient. So consider all cofinite subsets of natural numbers. Cofinite means that the complement of x, so n minus x, is finite. In the lecture about filters, we said that this is a filter. It doesn't have the empty set because its complement is n. It has the whole set n because its complement is empty, so finite. And it is closed under intersections and supersets. We already checked this. So by the main result about filters, it is contained in some ultrafilter. What kind of ultrafilter is this phi? Is it principal filter or not? Principal means that it is a collection of sets that contain one fixed set. No, it is not principal. Because we have a criterion, a necessary and sufficient condition for principal filters. For principal filters, a filter is principal if and only if we intersect all elements of phi, so all sets from phi, then we obtain an element of the filter. But here, let us intersect all sets that belong to phi. Among these sets, there are sets from psi, but the intersection of these sets is empty. Because we can consider these cofinite sets n minus the singleton k. They are in psi, and the intersection is of course empty. No natural number belongs to the intersection. So we know that if we take all cofinite sets, subsets of natural numbers, then the filter, the ultrafilter that contains all these sets, is non-principal. And in fact, the converse holds. If we have some non-principal ultrafilter over natural numbers, then it must have all cofinite subsets of natural numbers. So in our examples, in our next examples, if we say, let us take non-principal ultrafilter, this immediately implies that phi contains all cofinite subsets. And this is what we need, in fact, in our examples. So let us consider examples of some classes of mathematical structures. The class of all groups. We know it is finitely axiomatizable. We have 3 axioms for groups. The class of finite groups. Let us show that the class of finite groups is not finitely axiomatizable. Is not even axiomatizable. Not finitely, but we cannot even define it by an infinite set of formulas gamma. So let us use the Kessler's theorem. Let us show, so a class is axiomatizable if and only if it is closed under ultraproducts and elementary equivalence. Let us show that this class of models is not closed under ultraproducts. Let us take groups Zn for any natural number n, Z1, Z2, Z3, and so on. We will take the ultraproduct. Ultraproduct modular which filter, which ultrafilter? We consider the non-principal ultrafilter over natural numbers. So recall that such an ultrafilter contains all cofinite subsets. Okay, so we have groups numbered by natural numbers, indexed by natural numbers. And notice that groups are bigger and bigger and bigger. And we have a non-principal ultrafilter. Let us take the ultraproduct. This will be a mathematical structure. This will be a model. The first question is it a group?
Yes, by Walsh's theorem.
Yes, so each Gn satisfies the 3 axioms of groups. So the ultraproduct satisfies the 3 axioms of groups. So it is a group by Walsh's theorem. Next question, is it finite? Is it a finite group?
Well, no, because there are infinitely many sequences of these elements.
And so what? There are infinitely many sequences, but then we identify sequences that are the same on almost all on so we introduce the equivalence between sequences, and then we take the quotient set. So it is not quite obvious. So if we have simply the product, then of course we have, this will be an infinite. It will be again a group. We know that groups are closed under products. It will be a group. It will be an infinite group. Moreover, it will contain continuum many sequences. It contains in particular all sequences of zeros and ones. So it has continuum many sequences. But we take, we then collect clusters. So two sequences are equivalent if and only if they are the same on almost all indexes I. And it is not obvious that we obtain finitely many classes or infinitely many classes of sequences, or will it be countably many classes of sequences or continuum many classes? It's not clear. But we again can use Walsh theorem. Walsh theorem can help us. The first question is this group of size at least 2? Is it the case that this group has at least 2 elements, possibly more? Can we express this property by some first order formula and then use Walsh theorem? So let us write.
Maybe exists x1, x2, that x1 isn't equal to x2.
Yes, yes. This is the first order formula. It involves equality, but I said in the previous lecture that equality still satisfies Walsh's theorem. So Walsh's theorem works for equality as well. This is a simple exercise to check the details of Walsh's theorem for equality. So this theorem will hold on G if and only if it holds on almost all groups Gn. There exists X, there exists Y, such that X is not equal to Y. Which groups satisfy this theorem, this sentence, this closed formula? Groups number 2, 3, 4, and so on. So the set of indices n such that this group satisfies our sentence is the following set: 2, 3, 4, and so on. It is a cofinite set. Its complement has only the element 1. We start here n with 1 because G0 is not an element. It's not a group. So we start with 1. So it is a cofinite set. So it is in our filter. So from the viewpoint of our ultra filter, almost all groups satisfy this property, this first order property, this first order formula. So by Walsh theorem, the group G satisfies this property. And we can do the same for formulas that say there are at least n elements. There exist x1, xn such that they are non-equal. Which groups satisfy this sentence? The group number n, n plus 1, n plus 2, and so on. There are cofinitely many numbers n such that the group Gn satisfies this formula. So almost all groups have at least 10 elements. Almost all from the viewpoint of our filter phi. Therefore, G satisfies this formula. So for every n, our group G satisfies this formula. Therefore, it has at least n elements for every n, so it is infinite. So what do we have? We take finite groups, take some ultra filter, take the ultra product, and this ultra product is an infinite structure. It is even a group, but it is an infinite. So G does not belong to our class. So the class of finite groups is not closed under ultra products. Perhaps this is the main observation for all our examples. So it is not axiomatizable at all. Let us consider infinite groups. The class of infinite groups is of course axiomatizable. We need to take the axioms of groups, and these sentences, there are at least two elements, there are at least three elements, and so on. It is an infinite list of axioms, and its models are exactly the infinite groups. A model satisfies this list of axioms if and only if it is an infinite group. So this class is axiomatizable. The question is it finitely axiomatizable? Can we reduce this long list of axioms to finitely many axioms? Again, let us use the criterion, the necessary and sufficient conditions. This class of groups, this class of models, infinite groups, is finitely axiomatizable if and only if this class is axiomatizable and its complement is axiomatizable. Well, this class is axiomatizable, no problem. Let us consider the complement. What is the complement of the class of infinite groups? What are the structures that belong to the complement of this class?
Well, it's finite groups and something else.
Yes. So we firstly have finite groups, and secondly, any other structures that in the signature of multiplication, so in our signature, that are not groups, that do not satisfy the axioms of groups. So we have non-groups and finite groups. Why this class is not closed under ultraproducts? Let us use the same counterexample as on the previous slide. Let us take groups Zn. Let us take the ultrafilter, the non-principal ultrafilter over natural numbers. Let us take the ultraproduct G of groups Zn. So what do we have? Each group Zn belongs to this the complement of K, because it belongs to this part. Now we have the ultraproduct. Does it belong to this union? Does it belong to this part? No. We know that the ultraproduct is an infinite structure. Does it belong to this part? The ultraproduct of groups Zn. Does it belong to this part?
Oh, well, no, because axioms of groups hold in all.
Yes, because we know that this ultraproduct is a group, is an infinite, but still group. So it doesn't fall into this category, and it doesn't fall into this category. So we found some groups, some elements of this class over line K, so the complement of K, such that the ultraproduct is not in this class. So this complement is not closed under ultraproducts. So by the Kessler's theorem, it is not axiomatizable, the complement of K, and therefore our class K, so K is the class of infinite groups, is not finitely axiomatizable. So the conclusion, we cannot reduce this infinite set of axioms into finitely many axioms. can we define some class of groups such that neither the class itself nor its complement is axiomatizable? Here's an example. This is some combination of finite and infinite. The groups must be infinite, but something must be finite about them. Let us consider the period. Consider all groups that are infinite, but still for every group has a finite period. So there is a number n such that all elements from our group in this power n give us the unit. It is an exercise to show that neither k is axiomatizable nor its complement is axiomatizable. So you need to build to show that the class k is not closed under ultraproducts and the class not k is not closed under products. Instead of ultraproducts, you can simply think in terms of compactness. You can, in fact, reformulate our main result as follows. K is axiomatizable if and only if K is compact and closed under elementary equivalence. So instead of closed under ultraproducts, you can simply write compact. Because if K is closed under products, it is compact, of course. And if it is axiomatizable, then it is compact. Because every axiomatizable class satisfies compactness. It is an easy exercise, an easy consequence of the usual compactness. Well, in fact, it is in fact the consequence of this theorem. Yes, every axiomatizable class is closed under products, so it is compact. Okay, so in all examples, in fact, you could think in the more simple terms, not about ultraproducts, but about compactness. So here, for example, consider these sentences. There exist at least 10 elements. Consider gamma. There exist at least one, there exist at least two, there exist at least three. So this is an infinite set of formulas. Every finite subset is satisfiable in our class of finite groups, of course, because there are groups of 3 elements, of 4 elements, of sufficiently large elements. But the whole set of formulas is not satisfiable because it will imply that the group is infinite. So in terms of compactness, it is easier to solve these exercises. So you simply need to build some set of formulas gamma such that every finite subset is satisfiable in K, but the whole set is not satisfiable. And simply for the complement. But by the way, do you know any infinite group of the period 2, for example? Or maybe we say about, maybe there are no groups of this kind and nothing to say about. An infinite group with a finite period.
Maybe this can be some sequences of zeros and ones that the operation is addition over the field Z2.
Yeah, so basically this is Z2 times Z2 times Z2 and so on. So infinite product of the group Z2.
Yes.
This will be a group of cardinality continuum, but every element plus the same element is 0 plus modulo 2. Of course, similarly Zn and so on. So you can simply work with the groups Zn and so on to obtain both results. for fields, almost the same. All fields are finitely axiomatizable. Finite fields, not even axiomatizable, in the same manner as for groups. Infinite groups are axiomatizable, like here, but axioms of fields instead of groups, but not finitely axiomatizable, again, like here. For fields, we also have another property of fields, the characteristic, the smallest number p, such that 1 plus 1 plus 1 and so on, p times equals 0. For example, the field zp, where p is a prime number, is a field of characteristic p. And of course, there are fields that don't have this property. For example, the field of real numbers. We say that they are they have the characteristic 0. The question is the class of fields of characteristic p. Is it axiomatizable, finitely axiomatizable? Well, of course, it is finitely axiomatizable. We can simply say that 1 plus 1 plus 1 is 0, but for smaller number of units, it is not 0. The fields of characteristic 3, for example, 1 plus 1 plus 1 is equals 0, and 1 plus 1 is not 0. So this is the axiomatization of fields of characteristic 3. And now, similarly to this, some combination of finite and infinite. We consider infinite fields of finite characteristic. Firstly, think, do you know any example of such a field? We cannot take the direct product. Yes, we cannot take the Cartesian product because fields, the Cartesian product of fields is not a field. But there are, of course, fields like this, and the class of fields of this kind, neither this class itself nor its complement is axiomatizable. Again, an exercise like this. And there are, of course, examples in the very different field. For example, well-ordered sets. What is a well-ordered set? It is a linear set, linear ordered set, such that every non-empty subset has a minimal element. So this this definition is not first-order definition. Every non-empty subset, we need a quantifier over subsets. It is not a first-order definition by first-order formula. So we can suspect that this is not an axiomatizable class. And indeed, it is not axiomatizable. It is not elementary. And its complement is not elementary. Okay. So we have a hierarchy of classes. There are very simple classes, finitely axiomatizable. There are classes that are axiomatizable, but not finitely axiomatizable. There are also classes that such that their complement is axiomatizable, but the class itself is not axiomatizable. So these are two. So we have finitely axiomatizable, then axiomatizable, then co-axiomatizable. So their complement is axiomatizable, like here for finite groups. Their complement infinite groups is axiomatizable. And there is also a fourth family of classes. In fact, unions of axiomatizable classes. And in fact, this is all. The hierarchy stops here. We have four rooms of classes, four families of classes. And this class well-ordered set, it is not on the lower level. It is not finitely axiomatizable. It is not even axiomatizable. Its complement is not axiomatizable. So it is not in the room number 1, 2, 3. And moreover, it is not in the room number 4. It cannot be represented as the union of axiomatizable classes. So it is a very very non-elementary class in some sense. These and more and other results can be found in this book, Balance-Thompson, Models and Ultra Products, an introduction. In particular, you can find some more information about what is the room number 4, the union of axiomatizable classes. What is this? Do you have any examples of some mathematical structures that belong to this room number 4, but not to the room number 2 and 3, and of course not to the room number 1, finitely axiomatizable? And there are some more interesting theory about this hierarchy and so on. Okay, so this is the end of lecture, and we can discuss some questions if we have